For learning and sharing information, communication through sound is vital. A small change in the voice of the speaker giving a lecture contains a lot of information. When you don't pick up the message clearly, it will be a lot harder for you to understand the concept that is being explained. When enjoying live music, the tones and sounds produced by the performer will mix in the room and create harmonies. The properties of the room itself have a big impact on how the music is perceived by the listener. In this video, we will study the concept of reverberation in an auditorium designed for both lectures and live music. This lecture hall will serve as an example for explaining the concept of reverberation. Its stair-shaped seatings resembles the ancient Greek amphitheaters. To make sure everyone in the audience can hear the performance as well as see it, we have to understand the physics behind the sound. The reverberation time is defined as the time it takes for a sound to decrease 60 dB from its original level. So, looking at this graph, we can see that on the vertical axis there is a 0 and a minus 60 dB, which is how much the sound has to decrease. On the horizontal axis, there is an 1 and a 3, they are the position in time. Their difference represents the time it takes for the sound, given in the example, to decrease 60 dB, and this is the value for the reverberation time. To make it more easy to understand, let's see one example. Now, analyzing this example slowly, we can divide it in three parts. The first part is when the sound stops being emitted. It is when the source stops emitting the sound and the only thing that keeps in the air is the sound that is already there. Let's see the second part. The second part is when the sound has already decreased 60 dB, or, in other words, when its volume is largely reduced but not entirely. Let's see the third part. The third part is when the sound ceases to exist completely. The waves have all already been absorbed.
Reverberation is caused by sound energy being reflected from the walls, the floor, and the ceiling. When this happens, the sound energy will stay in the room. The more sound energy that stays in the room, the longer the reverberation time will be. If this reflection can be reduced, the total sound energy in the room will also be reduced. This will shorten the reverberation time and make it easier to perceive speech. Here we will show you two examples of materials with different sound absorbing properties. To the right we have a porous material with high absorption. This could be a piece of mineral wool of the same kind we often use for heat insulation. To the left we have a hard surface, in this case plaster on a brick wall. When the sound hits the wall on the left, the irregular surface will scatter the energy in multiple directions. Since the absorption is low, the reflected energy will be almost as much as the incoming sound against the wall. For the absorbents, it is a different case altogether. The incoming sound wave will split up inside the porous material. Here it will cause friction between the fibers of the material and the air surrounding these fibers. The kinetic energy of the sound wave will be transformed into heat. It is not enough to heat up a room in the winter time, but it will dampen the sound pressure in the room by stopping the reflection of sound waves. The amount of sound energy that is absorbed can be described by the absorption coefficient alpha, which depends on the material and the frequency of the sound. The alpha is a number between 0 and 1. 0 means no absorption, and 1 means total absorption and no reflected sound at all.
The high absorption of the surface materials in our auditorium, lead to a relatively short reverberation time. By identifying these materials and assigning them with absorption coefficients, we can construct a model of the acoustical environment in the room. With this model, design changes can be tested and evaluated. The risers of the stairs are covered with a heavy fabric. This will provide damping, especially in the high frequencies. The drapes covering the sides of the auditorium are made from a medium-weight synthetic fabric. The pleated sinus-shaped drapes have high absorption qualities. The reverberation time was measured using impulse noise. The impulses were generated by popping a paper bag and a balloon. After the impulse was emitted, the time it took for the sound level to decrease 60 dB was measured. Here you can see the measurements being performed using a paper bag. A long reverberation time will make spoken words mix together and make it more difficult to perceive speech. A short reverberation time will, on the other hand, give a toneless experience of music. For a good perception of speech, the value should be around 0.7 seconds. For music, 1.15 seconds is a better value. In our report, we have proposed design measures to achieve these target values. The hall will be surrounded by plywood walls covered with a pleated drape. The drapes can be removed when having musical performances, thereby gaining a longer reverberation time and a more pleasant musical experience.